Griffiths Electrodynamics, problem 2.21. Find the potential inside and outside a uniformly charged solid sphere whose radius is big R and whose total charge is little q. Use infinity as your reference point to compute the gradient of V in each region and check that it yields the correct field. And then sketch V as a function of R. Alright, so first we need, so to find the potential we'll be using this equation. So first we need the electric field in each region. And we've probably done that in earlier problems just by Gauss's law. So just as a quick review, let's go ahead and do it again. So outside, all right, again with Gauss's law, we, because of the radial symmetry of the sphere, we know what direction the electric field is going to be in, just the r hat direction. We just need to find the magnitude, and alright, so here's the integral we use for Gauss's law. Alright, but we, again, we just need to find the magnitude of E from this. Because of the spherical symmetry, the area vectors will all be facing along the radial direction as well. And this comes down to this sort of thing. So we just get this E divided by the total area of the sphere. Alright, so do outside first real quick, it's easy. So we know what A is, 4 pi r squared. And the total charge enclosed will be the total charge of the entire sphere, which they give us as little q. Alright, so this leads us to, well, I'll write it down here. We just divide right here. Q over 4 pi epsilon naught and then r squared. And again, we know the direction of this vector, so we go ahead and make it a vector, and it's in the r hat direction. So this is outside. Alright, if we go ahead and look at inside, we have the same thing. So 4 pi r squared is the area. Now, we'll still have this 1 over epsilon naught, but the tricky part is how much of this little q is contained in our, in the inside of our Gaussian surface. Well, it's just the ratio of the two volumes because the charge is uniform. So we have the volume of the small over the volume of the whole thing. The volume of the small is 4/3 pi little r cubed, and the volume of the big is 4/3 pi big R cubed. Alright, and the 4/3 pi cancels right out. So we have an E. I'll go ahead and leave 4 pi r squared on there for now. Equals little r cubed over big R cubed and epsilon naught. Alright, now we divide this through. We have E equals, alright, so the only difference, let's see, we have this r squared, which is going to cancel with 2 of the powers of r here. So we have a little r on top is all that's left. And then we have our 4 pi epsilon naught and big R cubed. And again, when we make this a vector, we know it's just going to be in the r hat direction. Alright, so here's our outside, here's our inside. That was fairly painless. And now, let's see, we'll get to the problem. So we're going to find the potential inside and outside. So let's start with outside first. So kind of the strategy for this problem is if out here is infinity somewhere, we're going to integrate in to the radius of the sphere, which is big R, right? And the electric field is all known by this equation on the outside. So we'll integrate this equation from infinity until we reach the surface of the sphere, at which point the electric field changes to this equation, even though, anyway, right? And so when it changes to this equation, then we'll do our second integral from the surface of the sphere into the center of the sphere, right? So if you want to know the actual value of a potential inside, somewhere inside the sphere, you have to add on what you calculated all the way from infinity to the surface, and then add to that what you calculated from the surface of the sphere into the point you're looking at. All right. So for the outside, we only have to do one integral. For the inside, we'd have to do two, except one of them is the same as the outside, so we can just add the answer on that we got before. So we'll start with the outside. So V out. Okay, so we have a minus here. Our origin is going to be infinity. And we'll go into this point R. Okay, for the outside, this R could be out here somewhere. It could be at any point outside up to, once you reach the surface of the sphere, then this is no good anymore. All right, so E dot dl right here. And we're in radial components, and our E for the outside is this. So we have Q 4 pi epsilon naught R squared, and that's on R hat, times by, and then we take the dot product of this with the dl. All right, so that's a dr R hat plus a bunch of other random stuff I can never remember, which I need to just derive for the theta hat and phi hat, but those don't concern us here because we don't have a theta or phi hat in here. So when we take the dot product, the components of the electric field in those directions is 0, and when you take the dot product, it kills the components over here too. All right, so basically R hat dot R hat is just going to give us 1, and all we have left over is this dr. So radial symmetry's our friend. All right, so Q 4 pi epsilon naught R squared dr is our integral to do. All right, so go ahead and bring out the constants, Q over 4 pi epsilon naught. And now when we integrate we're just doing R to the minus 2 power. So we raise it by 1, so it's R to the minus 1, and divide by a minus 1. And this is going to be, and we also have this minus sign out here. All right, so here's our expression. We just have to clean it up a little bit. So this minus sign will cancel with this minus sign, and we end up with constants out front, Q 4 pi epsilon naught. And we have a 1 over R, or R to the minus 1, minus 1 over infinity, which is 0. Okay, so why not? Let's write this on the new page. Let's see, out, which we just found, is equal to just have a q 4 pi epsilon naught r, right? It's a scalar, we don't have any component directions on it or anything. All right, so there's our V out. Now we'll move on to the V in. All right, so again, when our strategy here, we integrate to the surface, and then when we get inside, we'll be adding what we did out here plus what we do inside. So we'll have a term of this which is just the V out evaluated at the radius, right? Integrate all the way to the radius, and then we add that on to what we integrate inside, right? So here's that, and now we'll do our integration from big R into the point inside that we want. Okay, and then we have our E dot DL. And get down to a new sheet here. As long as we know where one is. All right. So let's just focus on this integral here for a sec. Now we move to our new electric field equation. So if I'll just write this integral out here so we know what we're doing. Again, in spherical coordinates, the radial component of dl is easy. It's just dr in the r hat direction, right? The radial component. And that's the only one that we're going to need here. The r hats will give us one, just like before. So what we end up with, big R to little r, we have this equation here now, which is little r over 4 pi epsilon naught big R cubed, and then dr. Right, when all the smoke clears from this dot product, all we're left with is dr. All right, so bring the constants out front. Did I forget it? I forgot a q, didn't I? When I did my Gauss's law. Wow. Okay. There's a q here, right? Because all I did was take the ratio of the volumes. All right. Big mistake. Q. Okay. And there's a q here. All right. Let's see. If you check your units, you'd know that was wrong. Okay. 4 pi epsilon naught big R cubed. Okay. Let's see. All right, we have our minus sign out here. All that's left to do is, so we're big R, little r, and we just have an r here to integrate. Well, that's about the nicest integration anyone could hope for. All right, our original problem right here. So we move to a new page. All right, so minus q 4 pi epsilon naught big R cubed, and now we have an r squared over 2, and this is evaluated from big R into little r. Okay, so minus q 4 pi epsilon naught. I'm going to hold off on the r cubed for a sec. Well, I'll just bring it inside these parentheses so we can see what simplifies. So we have little r squared over 2r cubed minus big R squared over 2r cubed. All right? I think I did that right. Okay, well, this will cancel with 2 of those, and we can bring the 2 out. We can even bring this whole 2r out if we want. Why not? Let's do it. And, you know, hope I didn't mess up I may have missed a minus sign in here somewhere. We'll see what happens when we get there. All right. So I'm just going to bring the minus sign into this as well, right? So this. Okay. Q over 4 pi epsilon naught, and we're going to bring the 1 over 2r outside. So here, this we brought this out, so it's just a 1 here, and then minus little r squared over big R squared. All right, I think this looks right. Okay, what do we have now? Compute the gradient of V in each region and check that it yields the correct field. Oh, right, we didn't tie something down here, which is we need to find our actual V in. Remember, all we were doing was finding this term right here, right? So we just have to add V out to it. So V in equals this V out. So Q over 4 pi epsilon naught R plus this thing that we already did, and we included the minus sign, so we just add this right here, plus Q over 4 pi epsilon naught 1 over 2r, that's a big R, 1 minus r squared over big R squared. And again, hope I didn't miss a minus sign anywhere. Okay, so I'm going to go ahead and put a box around this so it matches our V out here. Okay, now we'll take the gradient of these. And again, the gradient in spherical coordinates is all messy, but the r component of it is just dy dr in the r hat direction. Let me double check that in the front of the book, because make sure there's no minus sign or anything. No, we're good. Okay. Just make sure. All right. Okay, so let's do it. And again, with this radial symmetry that we have, the theta and phi terms of the gradient, there's derivative with respect to theta, derivative with respect to phi, and since our potentials don't depend on either of those terms are going to be 0. So that's why we can focus only on the r component here. All right, let's do the outside first. All right, so E out should just be equal to the negative gradient of V out. All right, and when we take the gradient of, let's see, I'm out of time on my, pretty much out of memory on my memory card, so just go till it runs out and then edit in the rest of the video. Q, put the constants out front, Q 4 pi epsilon naught, and then we just have a d by dr, which this can be a total derivative since that's the only thing we're differentiating with respect to 1 over r, and the r hat direction, and there's this minus sign as well. Okay, so, right, where were we? We were taking the derivative, all right, the gradient of this potential here. Right, so when we have a 1 over r, it's just an r to the minus 1, right, so when we take the derivative of this, we just get a -1 out front and r to the -2. So basically this minus sign is going to come out front. And cancel with this one. So we'll just have a q over 4 pi epsilon naught. And then, so, right, this minus sign is canceled with that one, and then we have just an r to the -2, so 1 over r squared. In the r hat direction, this is our outer electric field, which, if we can find what page that was on, it should match up just fine. Obviously, right? It's just the field of a point charge, right? So here it is. Here's the outer field. Matches up, so that one checks out. Now, while I was emptying my memory card, I also found a mistake that I made earlier on with the field in here. I wrote a little r down here, but if we remember, what I was supposed to do was evaluate this at big R right here, right? So this little r should be a big R. Okay. Now, we're almost done. We have to now, shuffling the papers, we have to now find the electric field inside using this minus the gradient of V on the inside, right? So same as what we did before, except now we're going to be using our expression for the potential on the inside, which is just right down here. Trying to get my papers together. Okay. All right, so and again, there's only the r hat component, so we're just taking the, and it only depends on r, so we can take the full derivative. And this is in the r hat direction, and what goes in here is this v. So constants out front, q over 4 pi epsilon naught. And we can actually, now that this is a 1 over big R, and I fixed that mistake, we can combine these things inside here. So we have a 1 over R, and if I, well, all right, let's go ahead and we'll have a 1 over 2r still factored out, right? So what do I need now? From this term, we're going to have a 2 inside plus a 1 minus the r squared over the big R. Sorry for the extra noise. Okay, so right, when we take this derivative, these are just constants and they won't matter. So we're going to end up with, and I'm going to bring, right, so like I said, these ones will go away. And this minus sign I'm going to bring out and cancel with this minus sign. And I'll also bring the constants out front. A lot of stuff at once. Q over 4 pi epsilon naught. 1 over 2r. This minus sign canceled, and we just have a d. Right? If we don't run out of battery, we'll be good. Okay. R squared over big R squared. All right. So we take this derivative. We'll just get a 2r on top, and a big R squared on the bottom. And this 2 and that 2 are going to cancel. And we'll just be left with q over 4 pi epsilon naught. Like I say, this 2 and that 2 are going to cancel. We're just going to bring this r in with this r, and we have the little r on top. And when we bring this r in with these 2 r's here, we end up with r cubed on the bottom. And that should be the same as our electric field for the inside, right? So this right here is the same as this right here, so that part checks out too. All right, the final part is to, if I can find a clean piece of paper and if I can gather the pieces that we're going to need. The final part is to just sketch V as a function of R. All right, so we have some point here where it's going to change its behavior, right? And its value at that point, basically outside of this, it's just going to drop off as a 1 over R. So I may have not drawn that quite, but you can use your imagination. This is a 1 over R dependence out here from this. And it's going to match up with what's here on the inside. So if we evaluate this at big R, then basically this term's going to go to 1, and the 1 minus 1 is 0, right? It will match up. The potential is always continuous, right? So it has to match up, and we're just going to get this. So at this point we have a Q over 4 pi epsilon naught big R at this point right here. All right, and inside that, well, let's take it when we go to 0. When little r is 0 here, then we just have a Q over 4 pi epsilon naught. We have a term of 1 over big R, and then we only have this term here, which is 1 over 2 big R, right? So this is equal to 3 halves, so 3 over 2R, 2 big R, Q over 4 pi epsilon naught. So, and so this is the value at V equals 0. It's probably up here somewhere, actually, right? Somewhere. So Q over 4 pi epsilon naught. My battery doesn't die now. Who knows what's going to go on now? 3 over 2 big R. And that's at this little point right here. Okay? Yeah, these problems are using a lot of paper. All right, now, and it's, so from that point, it's just going to drop off as an R squared, 1 over R squared. Is that right? Where's my, what a mess. Okay, here we are, right? So from that point, the part that's changing is right here. We're dropping off as not over, not 1 over R squared, but as R squared, right? So basically it's what is this? It's an upside down parabola. Okay, I hope I'm doing this right? So if you can imagine kind of an upside down parabola like this isn't very, to scale, I guess, but you can use your imagination, right? This goes as a minus R squared, and this goes as a 1 over R, right? So we kind of have this upside down parabola here. Maybe it's a little more like that, but that's kind of just gives you an idea of what our potential looks like.